Thank you very much, Jonas, and thanks everybody for coming. So what I want to talk today is about the use of Gaussian process regression, and in particular convergence properties. So I'm going to start with a very brief problem formulation, so just so that we're all clear on the problem that I'm trying to solve. I'm then going to tell you how you can solve it using Gaussian process regression. And I'm then going to, as I said, talk about convergence properties of this method. So some convergence results, and then in the end, some conclusions. Right. So the problem that I want to solve is the following. Okay, so I'm interested in function reconstruction. So I assume that I have some data on some unknown function f. And function f here is just a function from some domain u into the reals. And I want to reconstruct that function given some function values. So I assume that I have these capital N function values of the function f. That is all the information that I have about f, and I want to reconstruct the underlying function from that. I'm going to solve it in a Bayesian statistical framework, which means that my answer is going to be a posterior measure on the unknown function f conditioned on my observed data. Yeah, so because I get the posterior measure, that then allows me to do some uncertainty quantification in the recovery, as well as getting an estimate of my unknown function f. And the thing that I'm interested in, as I said, is kind of convergence of these methods. So I'm interested in what happens as I get more and more function evaluations, and in particular what happens as my number of function evaluations goes to infinity. And I'm interested in the question, if n goes to infinity, do I actually recover the true function f that is generating my data? Okay, so in this case, that is a type of posterior consistency. So as I said, because I'm solving it in a Bayesian statistical framework, my answer is a probability measure on f given y. And I'm interested in the questions whether the mean of this posterior recovers the true function f. So does the posterior mean converge to f? And does the posterior kind of concentrate around my true f? So does the posterior variance go to 0? Okay, so that is the problem that I'm interested in solving. The way I'm going to solve it is, as I said, in this Bayesian statistical framework, and in particular using Gaussian process regression. So Gaussian process regression is just a particular instance of the Bayesian framework where the prior distribution is chosen as a Gaussian process. So we're going to do the standard thing that we do in the Bayesian approximation framework, where we choose a prior distribution on f, and then we obtain the posterior by conditioning on our data. So as I said, for the prior, we choose a Gaussian process on f. If you're not that familiar with Gaussian processes, I've given the definition here. So modeling the function f as a Gaussian process means that at every point ui in the domain u of the function, we now have a Gaussian random variable. The mean function of the Gaussian process, which is this first term here, gives you the mean. So in this case, for simplicity, I've chosen mean 0, which means that the expected value of f at any point ui is 0. You can also do everything with non-zero mean, so everything that I say also holds non-zero mean, if you're interested in that. And then the second term here, k, is the covariance kernel, which gives you the covariance between f at a point ui and a point uj. Right? So this is the mathematical definition. I've also given you a more kind of visual explanation here. So what you're doing is here, you're providing a mean function, which in this case is the bold red line at 0. And then your functions kind of stay close to this mean function, and they fluctuate around the mean function depending on the size of the standard deviation that you put on it. So the samples that you would get would be something like this. So you can see the samples all stay quite close to the mean 0, and then they fluctuate around this mean function. Okay. So this is then our prior distribution on the unknown function f. And then, as I said, we do the usual update step in the Bayesian framework, and then we condition the prior distribution on our observed data. So we're now looking at the distribution of our unknown function f given these function values that we had. And as I said, it's just the prior conditioned on the data. The nice thing about Gaussian process regression is that the posterior can be written down in closed form. Okay, so in general, this conditioning step is quite complicated, and you might not be able to write down the conditional distribution explicitly. But if you do it with Gaussian process regression, you can. So you know that the posterior is also a Gaussian process, and you can write down the mean function and the covariance function explicitly. I've given you the formulations here, then it is not really that important exactly what they are. What's important is that you can actually write these down explicitly so that you have a closed form expression for the posterior. So what you're doing is, with our data, we now have these function values, say at these 4 points here, and then we're conditioning everything on passing through those function values. So used with the conditioning, we now get a new mean function, which always passes through the function values. And we're also updating our covariance, in particular the covariance around the points where we have observed the function is 0, because we know what the function is here. So there's no uncertainty or variance here. And similarly, all the sample paths that we get from our conditioned Gaussian process posterior also pass through all of the function values. Right. So this is the process that we want to do. So this gives us then a posterior probability measure on the function f given our observed data y. And I've told you what the answer is. I've told you you can write down everything explicitly. So you might think that we're done. Okay? But the problem in most applications is really how to choose the prior. Right? So once you have the prior and you have your data, you can then get the posterior just by conditioning the prior on the data. But the challenge in most applications is really choosing what the prior should be. Okay? In particular, you need to choose the prior so that you get kind of the right properties of f. Okay? So in particular, the covariance kernel k that you choose in your prior, that is going to determine a lot of properties of the Gaussian process. So I've given you a couple of examples here. So one thing that it determines is, for example, smoothness. By smoothness, I mean differentiability, how many derivatives the sample paths are going to have, and also the mean function is going to have. So I've given you some examples of processes here. Okay, so in the top row, I've actually generated samples from a Gaussian process where the sample paths are only Hölder continuous with exponent 1/2. So these are quite rough paths, and the paths are not even differentiable. Whereas these two examples here come from a Gaussian process where the sample paths are analytic. So these are infinitely differentiable sample paths. And so you see that you get very different functions here. Right? So that is something that's determined by the covariance kernel. There's also the contrast. So by the contrast, I mean the difference between the largest value and the smallest value in the domain. Right? So this is kind of a horizontal length scale, and it determines kind of the size of the fluctuations that you get. So it's the difference kind of between the largest and the smallest values. There's also the typical length scales of the fluctuations. So this is something that you might know as the correlation length. So this is a kind of typical length scale that governs how fast your samples oscillate or fluctuate. And so in this example here, for example, this has quite a long length scale. So you only get fluctuations or variations on very long length scales, whereas this Gaussian process here has a shorter length scale, and so you can see that the length scale at which you get fluctuations is a lot shorter, and you get a lot more fluctuations over the same domain. Okay? So these are all things that are determined by the prior, and usually there's some hyperparameters or some parameters in your covariance kernel K which govern what these things are. Okay. In general, there's also a lot of other properties that the covariance kernel determines, such as periodicity and stationarity, but I'm not going to talk about those today, and I'm mostly focusing on these things here. Okay. So the challenge is then that these properties are usually not known a priori, right? So your function f is unknown. All you know about f are these function values that you observed. And so things like how smooth your function is, or kind of the typical length scales that you have, is something that you don't really know a priori. Okay, so that is really the challenge. So what you then have to do is you have to think about how you define the prior and how you do this Gaussian process regression of getting the posterior on f given the data y. Okay. So what we do is we do an empirical Bayes, or also known as a plug-in approach. So you could try and do a full hierarchical approach where you integrate out these hyperparameters in the kernel, but that is usually too expensive. So it's not analytically tractable and too expensive to do in practice. So we do this empirical Bayesian approach where you use the function data that you have. So you use your point evaluations to estimate any hyperparameters theta that you need. So as I said, these are typically parameters that tell you what the smoothness is and the contrast and the length scales and things like that. So you use your function values to obtain estimates of any parameters that you need, and then you just plug this in to the usual posterior distribution, right? And then that gives you your posterior on f, right? So you just choose in this posterior here, you then just plug in your estimates for the hyperparameters. How you find these hyperparameters is not really important for the analysis that I'm showing you. So that is a difficult question on its own, how to do this. You can do maximum likelihood, maximum posterior estimation, cross-validation, whatever you like. So as I said, our results are not dependent on how you estimate these parameters. And then what I'm interested in is what conditions I need to get this posterior consistency that I was talking about earlier. So what conditions do you need for the mean to recover the true function f, and for the posterior variance to go to 0? Okay. So what we're going to do to answer those questions is use results from approximation theory and numerical analysis. Right? So just saying again, what I want to show is that the posterior mean converges to the true function and the posterior variance goes to 0. Okay. So what we do is, as I said, we use results from numerical analysis. In particular, to show this, we note that the mean is essentially an interpolant of f. Okay? So to see that, we go back to the explicit expression that we had for the mean. Right? So remember, I told you for the mean, for the posterior mean, you do actually have an explicit expression. And there's two properties which are important. So one is you can show that the mean is a linear combination of the kernel functions. Okay? So there's a known coefficient vector alpha, such that you can write the mean as this linear combination. So it's a linear combination of these kernel functions k. And it is an interpolant, so that comes from the conditioning, because you're doing this conditioning, and you can also see it from the explicit expression. So at these points un, where we did observe our function values y, you do have an interpolant of your function f. Okay? So these two combined then just means that you have a kernel interpolant, so it's an interpolant, and the basis functions are these kernel functions. In special cases, you get back to radial basis function interpolants. So if your kernel k is isotropic, which means that it depends on the two locations u and u prime only through the Euclidean distance, then you get a radial basis function interpolant. Okay? So to show convergence of these Gaussian process regression methods, you can use results from scattered data approximation and radial basis function interpolants. Okay. So the kind of convergence that you get, in particular the rates that you get in n, will depend on the precise setup that you're working with. and in particular on the specific choice of the prior covariance kernel K. So you'll see here that the prior covariance kernel K takes the role of the basis functions, right? So the M is a linear combinations of the K, so the K's kind of take the role of the basis functions that you're choosing for your interpolant. Okay. So the results very much depend on K, and I'm now going to show you two different specific examples which are frequently used. So one of the examples that is very often used is the family of Matern covariances. So this is a parametric family of covariances. So they have three different parameters, which are these hyperparameters that I talked about earlier. So there's one parameter which governs the contrast. So this is the sigma squared parameter, which is just a multiplicative factor here. So that is the marginal variance. So that governs the kind of size or the amplitude of the typical samples. Then there's the correlation length lambda, which is so the correlation length or the fluctuation length scale. So this is the one that governs how on what scale you get typical fluctuations. So if your lambda is very large, then you get fluctuations only over very long time scales. And if the lambda is very small, then you get very oscillatory behavior. The final one is the the nu, which is the smoothness parameter, and this is directly related to how many derivatives your samples are going to have. So the nu governs the smoothness in that way. Okay, so generally this formula looks quite horrible. It does simplify for some particular choices. So when nu is equal to 1/2, you get this exponential covariance function. So you might know that as the covariance function of the Ornstein-Uhlenbeck process. And when nu equals infinity, on the limit as nu tends to infinity, you recover this Gaussian covariance function. So the difference between this one and this one here is that we have a square of the norm inside the exponential here. And so this is a much smoother function. All right. So this is something that is very often used in Gaussian process regression to give you the results on the convergence as n tends to infinity. I need to define two quantities here. Yeah, so the first one is the fill distance. So with these points un, which are our design points or interpolation points, so these are the points at which we have observed our function f, at which we have the function values. You can then define this fill distance. The fill distance is the measure of how space filling your points are. Yeah, so if you want the fill distance to be small, then your points need to be quite evenly spread out over the parameter space U. What you're doing is you're looking at the supremum over all possible points in your parameter space U, and then the infimum over all of your design points, and then the distance between U and UN. So you're looking at how far can any point U be away from any of the design points. Okay. So you can also interpret this as the radius of the largest ball in U, which does not contain any of the design points. Okay, so it's really a measure of how evenly spread your design points are in the space U. And typically you would get this kind of behavior for the fill distance. So if you have n points in du dimensions, so the du here was the dimension of my parameter u, then you would get a rate of n to the minus 1 over the dimension. Okay, so this is something that decreases with n. You also need something which is called the mesh ratio. The mesh ratio measures something that is a bit different. So it measures how uniform your points are. So in the numerator, you actually have the fill distance. Right? So in the numerator, we have the fill distance h dn. And in the denominator, we have the minimum distance between 2 points. Okay? So what happens if you have two design points or two interpolation points that are very close together, then your mesh ratio will be very large. Okay, so even if the points are quite well spread out and you cover the whole of U, so the numerator is small, if you still have 2 points that are very close together, then the mesh ratio will be very large. And so this really measures how uniform your points are. Okay, and the mesh ratio is something that is either constant, so in the best case it's constant if you have uniform points, or it can also be something that increases with n if you have point sets where it is very likely that 2 points will be very close together. All right, so this is the result. It looks a bit complicated, so let me try and go through this. So here I'm looking at the error between my true function f and the mean of the Gaussian process regression with the estimated hyperparameters, measuring the error in the L2 norm. We can also do other norms, and then you get this result here. So there's these two things that depend on n, the fill distance and the mesh ratio. This is the part that decreases in n, right? So as you get more and more points, you're filling your parameter space more and more well. And so this is the part that decreases in n with the fill distance. And then you also have this potential factor here that comes from the mesh ratio. And this is essentially a penalty term, which I'm going to come back to later on. Okay, so this result holds for any function f. So no matter, as long as your function f is in this Sobolev space here, if you're not that familiar with Sobolev spaces, assuming that my function essentially has mu plus d over 2 derivatives. Okay. The rates that you get depend then on both the true smoothness, right? So the mu that enters here and here, that depends on the smoothness of f. So that's kind of the true smoothness. And then you also have the estimated smoothness. So the mu star here is your estimated smoothness parameter that you have from the data. Okay. And so the rates that you get really depend on how well you're estimating your smoothness parameter. Okay. You do get optimal rates if you have the correct smoothness. Okay, so this is optimal in the sense of information-based complexity, estimating a function with this smoothness in terms of n function values. If you're not estimating it correctly, then you might not get the optimal rate. So in particular, if you're underestimating the smoothness, then you don't get the optimal rate here. And that's because you end up using basis functions which are less smooth than your function f. If you're overestimating the smoothness, then you might have to pay this penalty here. If your points are not uniform, then you have this mesh ratio that was increasing in n. And so you're essentially then paying the penalty for using basis functions k that are smoother than your function f. Okay. Just very quickly, so I was a bit surprised at how little assumptions you needed on the estimated hyperparameters. So essentially all you need is that they are uniformly bounded away from 0 and infinity. The estimated variance and length scale actually only go into the constant. The only thing that influences the rate is the estimated smoothness. I've here written down the result in the case where you get convergence, but you don't need convergence, and you can also work with the lim-infs and the lim-sups. Right. So I'm already running a bit out of time, so I'm just going to quickly show you this last result. So the one of the disadvantages of this setup that I talked about here is that you do get quite a bad dependence on the dimension. Okay, so this fill distance here usually goes like n to the -1 over the dimension, and so the convergence rates that you get here, and particularly also the optimal convergence rates, do deteriorate quite badly with the dimension. Okay, so that is something that is known if you're working with these kind of standard isotropic Sobolev spaces. And I said these are the optimal convergence rates. So that you deteriorate with dimension is quite natural in this setup. You can get better dependence on the dimension if you're working in these spaces of dominating mixed smoothness. So these are Sobolev spaces, which are tensor products of one-dimensional Sobolev spaces. In that setting, you have stronger control on the mixed derivatives. So that's where the name dominating mixed smoothness comes from. I don't have that much time to talk about it, but essentially, yeah, once you switch to these kind of spaces of mixed dominating smoothness, as I said, they're tensor products of one-dimensional Sobolev spaces. So you then end up assuming that you have a tensor product domain and also working with a tensor product type kernel. So you just have the product of one-dimensional return kernels. Then if you choose your design points or interpolation points as a sparse grid, then you can show that you get convergence rates which are dimension independent up to the log factor. Right? So then you can show that for this here, for example, you get a rate that is independent of the dimensions. The alpha here only depends on the smoothness and the estimated smoothness. It's independent of the dimension, but you do get the dimension coming in through the log factor here. Okay, so changing to this setup, you can get slightly much better dimension dependence. All right, so yeah, that was really all I wanted to say. So we use Gaussian process regression to solve this problem of recovering the true function f, giving n function values. I showed you that it does work in surprisingly under surprisingly mild conditions, that you do get convergence. Also, when you kind of misspecify the prior, so you don't have the correct smoothness, or you have the learning of hyperparameters as well. And if you're interested in more details, I will point you to this paper here, and I'm happy to take any questions if there are any.